Okay, what I'd like to do now is to focus on these two velocities that a wave packet can have, group velocity and phase velocity. I want to define them, and then we'll consider a few examples of systems where the group velocity and the phase velocity are different. All right, so we've just seen that if the wave speed depends on frequency, then a wave packet will its shape will change as it propagates. Okay, and in general, that we've seen that the envelope speed which we'll call the group velocity, will not equal the speed of the wavefronts. What's called the phase velocity. Okay? And I'd like to define these two terms and then investigate some systems. Now here, I'm just going to state first that the phase velocity of a wave is just equal to that quantity that we've always called the speed of a wave. It's f times lambda. Okay? Or writing f as omega over 2 pi and writing lambda as 2 pi over k, you can see that the phase velocity can also be written as omega divided by k. Okay? It means the same thing, but physicists like omega and k. So that's the phase velocity. It's what we've always called the velocity of a wave. The group velocity is something different. And it turns out that the group velocity, the envelope speed, is given by the rate of change of omega with respect to k. Okay? Which is a slightly different relationship. In fact, it gives us a way to think about a system. We could make a graph of frequency versus wavelength, or we could make a graph of omega versus k. And what we'd find is that if omega is proportional to k, as it is for light waves or ordinary sound waves moving through air under most conditions, then this would look like a straight line. And you can see immediately that in this case, the phase velocity and the group velocity would be the same. Okay? And since that describes most of the waves that we come into contact with, sound waves and light waves, it seems very natural that there should only be one velocity. On the other hand, if the relationship between omega and k is not linear, but is, say, looks like this, oops, then the group velocity and the phase velocity will not be the same. If we pick some point on the curve like this one, you can see that omega over k is that, but the slope of the curve at this point, oops, is something completely different. Okay? And this one, the slope of the curve gives us VG, whereas the omega over k itself gives us VF. So these won't be equal if the relationship between omega and k is not a straight line. Okay? So this kind of dispersion occurs in many different systems. It occurs in water waves. It occurs in light waves when they move through a medium like glass, where the index of refraction depends on frequency. And turns out it occurs in matter waves. And that's why we're investigating this. Here, let's look at an example and consider water waves. Okay? For waves moving through deep water, it turns out that the relationship between omega and k looks like this. Omega is equal to the square root of g, acceleration of gravity, times k. Okay? So the speed of water waves depends on their wavelength, and we can write we can express that relationship here. Okay? So let's see what the phase velocity is for water waves. Okay? So for water waves in deep water, that's what these are. This is omega over k. And so it's square root of gk divided by k, or square root of g over k. All right? Very good. What about the group velocity? The group velocity is derivative of omega with respect to k. And looking at this expression here, we can see this will be, well, let's see, we'll have square root of g times 1/2 k to the minus 1/2. That is 1/2 times the square root of g over k. Okay? There we are. So, as promised, in this case, the group velocity and the phase velocity are not the same. In fact, as you can see, Vg is 1/2 the phase for water waves. All right? And that means as waves move through deep water, a wave pulse will spread out as it moves. Okay? Perfect. Here, I want to show you a piece of video. 1 second. Okay, so this clip shows a motorboat moving through the water. And when it does, its wake initially will be a kind of wave pulse. And then we can see how the wave pulse shape changes as the wake moves out towards the sides of the river. So this was filmed on the Mississippi River from one of the bridges nearby. Here, let's take a look. You can see a wave pulse, and now it's going to evolve in time. Notice how out on the fringes, we have long wavelength waves, whereas close to the center, the short wavelength waves are lagging behind. The long wavelength waves are moving faster than the short wavelength waves. That's wave dispersion. And it's precisely what we predicted from the group velocity and the phase velocity. Okay. Very good. Well, now let's look at a second example. Let's look at matter waves. All right? And actually, we're going to focus on non-relativistic matter waves associated with non-relativistic particles to keep things simple. Okay? All right. So in this case, the phase velocity for matter waves should be lambda times f. Okay? Using the de Broglie relationship, we know that lambda is the same thing as h over p, and f is the same thing as the energy over h. Canceling out that factors of Planck's constant, we have energy over momentum. In the non-relativistic limit, the energy, the kinetic energy, is 1/2 mv squared, okay, or 1/2 p squared over m. So that means that the phase velocity is 1/2 p squared over m divided by p, or 1/2 p over m, or using non-relativistic formula for momentum, we have mv over m, or 1/2 of the classical velocity of the particle. So there we are. The phase velocity associated with a matter wave is 1/2 of the particle's classical velocity. And, well, that's kind of weird, isn't it? It tells us something. It tells us that the velocity of the wave fronts in the matter wave, that's not connected with what we normally think of as the velocity of the particle through space. It's something else. Here, it's 1/2 of that. On the other hand, if we look at the group velocity, we'll find something different. The group velocity is the rate of change of omega with respect to k. And if we like, we can write that as, well, omega is just the energy divided by h bar, and k is just the momentum divided by h bar. And so, canceling out the h bars here, we find that this is rate of change of energy with respect to momentum. And now, substituting for the energy, we get the following. Well, when we take the derivative of this, we get 2 times 1/2 p over m. So we get p over m, okay? And since p is m times u, the m's canceled, and we find this. Okay, very good. Well, what has this shown us? This shows us that the group velocity of the wave packet, that has the same magnitude as what we ordinarily think of as the velocity of the classical particle. So if we think of a particle, like an electron moving through space at some velocity, then that velocity is the group velocity of the wave packet. That is, if we draw a wave packet to represent our electron here, like so, then it's not the velocity of the crests that matters. It's the velocity of the envelope of the wave packet, the whole pulse as it moves through space. That's what we want to track. All right? So here we've introduced group velocity and phase velocity. we've shown that in dispersive systems, these are generally different. We looked at two examples, water waves for water traveling through, waves traveling through deep water, and found that we get different results. And then when we look at the propagation of water waves, we can see, yes, indeed, they do exhibit dispersion, and the group velocity does not equal the phase velocity. Finally, we considered the really important example for us. We considered matter waves. And here, when we examined the phase velocity and the group velocity, we found that it's the group velocity, the velocity of the envelope of the wave packet, that corresponds to the classical notion of velocity of a particle. All right, I think we'll stop here.